Today we're going to talk about absolute extrema, which builds nicely onto last night's topic of relative extrema. And so tonight we're going to be looking for absolute maximums and absolute minimums. The number one difference you're going to see tonight is that we're going to limit ourselves to a closed interval. Okay, so instead of going from negative infinity to positive infinity, we're just going to look at a snapshot, a very specific section of the graph within the interval from A to B. And so our first graph sets us up nicely. We're saying we're starting at x equals A, ending at x equals B. And within this interval, what we've noticed here is we've got a relative min right here, which reinforces what we did last night. We've got a relative max. This happens to be a relative min as well. And what we're going to learn is that a individual point can be both an absolute and a relative. So I would classify that point as both. And then the big difference tonight is we are going to consider the endpoints, and we're saying if I considered all the points, this right here is the tallest point on the graph. It's got the biggest y value, and so we're going to call that the absolute max. But this one right here is not a relative max, and I want to stress tonight that relative extremas that we studied last night can only occur within the interval. They cannot occur at the endpoints, but the absolute max and absolute mins could possibly occur at the endpoints. Let's take a look at a second graph here. Again, we're restricting ourselves to a finite interval. We'll say it starts here and ends right here. And within that finite amount of space, we're going to say this is our tallest point right there. And you see they've classified it as a local max. And they specified there just for fun that the derivative at point D is undefined because of the cusp-like behavior of the graph. But I'm going to go one step further and say, you know what, that's also my absolute max. So again, we're saying a certain point that occurs on the inside of the interval could be possibly both a relative and an absolute max. Now within that same interval, I'm going to say that this bear right down here is my absolute min, and just happens to also be a local min. And in this case, the endpoint on the left and the endpoint on the right didn't become a key factor because neither one was the tallest nor lowest point on the graph. One more graph here before we dive in and go further. Let's say my interval starts here and it ends at this endpoint right here. My absolute max, the single tallest point on the graph, is going to be my left endpoint, absolute max. And then again, we've got relative min, relative max, absolute min, and we're going to say that's both an absolute and a relative. It's both. Relative max, relative min, and this guy's just kind of a nothing. He's a dud. Okay, we're going to introduce you to the extreme value theorem, and similar to the intermediate value theorem, this does fall into the family that we call existence theorems, and we're basically going to prove the existence of an absolute max and an absolute min. And we're just saying if f of x is continuous, so there's our prerequisite, on the closed interval from A to B, if it was discontinuous after B or before A, we wouldn't have a problem with it. We would just casually ignore that. Then f of x must, let's really emphasize this word, it must have an absolute maximum value, and it must have an absolute minimum value as well. And basically all we're saying is when you consider this finite section of the graph, somebody's got to be the tallest point and then somebody's got to be the minimum point. And on this particular graph, I would say my absolute maximum value, now catch that, with the word value, is referring to the height of the graph. In other words, the y-coordinate is typically going to be our answer. So we'll say the maximum, and I'll throw the word absolute in there, value is 44, okay? And we'll also say that the absolute minimum value is, let's see, right there, negative 145. Now, with that being said, you may be challenging this theorem, and maybe you're posing the idea of maybe f of x is continuous, but it happens to be a constant, like maybe f of x equals 2, and you're picturing that graph, and you're saying, okay, the graph looks like this, and if I said, okay, there's A and there's B, I disproved this theorem because I created an interval that doesn't have a max or a min. Well, you do have a max. The maximum value is 2, and the minimum value happens to be 2 as well. So it's a rare instance where you do have a max and you do have a min, they just happen to be the same value. Now I want to take our time here before we dove into an equation and just really practice our graphical approach just so we're all visualizing the same thing. And then we're saying from -2 to 5, so I'm starting here at -2 and I'm casually ignoring everything that preceded the -2. And then we're cutting it off at 5, and anything beyond that 5 is not considered as well. So within that picture, now it kind of appears that we have a tie. We've got a maximum value of 4 here as well as over here. Now it doesn't actually matter how many times the graph achieves that height. We're still going to say that the absolute minimum, I'll start here, max value equals 4, and it occurs at 2 locations, x equals -1 and at x equals 5. But we still say the maximum value is 4. Then on the flip side, the absolute minimum value is going to be -4, and it happens to occur at x equals 3. So we could have, then just for fun, this would also be considered a relative max. This would be considered a relative min as well. Real quick, we'll try one more here. Closed interval is from -5 to 5, so we'll cut it off right there, and looks like 5 comma -16 might be down there. And certainly within that interval, the function's continuous, so the extreme value theorem applies. And I'm going to say my maximum value is 7, and it happens to occur at x equals 2. And my minimum value is way down here on that right endpoint, happens to be -16, and that occurs at x equals 5. Well, unfortunately, the problems won't quite be that friendly on the AP exam, and instead of giving us a graph to work with, they're probably going to give us a function, and they won't let us use our calculator on these types of problems. This will be on the non-calculator section. So we want to talk about how are we going to find the absolute max and minimum values in these cases, and we're going to use a technique or a method called the closed interval test. Okay, yesterday we learned the first derivative test. Today we're going to learn what's called the closed interval test, and basically we start off by finding the critical numbers within the set interval. We're going to use then the first derivative test from yesterday, and what's that going to do for us? Well, it's going to help us determine which intervals are decreasing and which ones are increasing. And by looking at which intervals are increasing and decreasing, that's going to help us determine the candidates. I really like the word candidates for the absolute max by considering the critical points and the endpoints. Maybe that's the number one difference between yesterday and today is now that we're dealing with absolute extrema, the endpoints are a significant player in this game. Yesterday they were a non-factor, today they could be a big factor. We're then going to take those x values that were the candidates and we're going to plug them into the original function, okay, the original f of x, to determine the maximum value, because remember, f of x, when we plug x values into that, it tells the output is the y value, which is the height of the graph, and at the end of the day, that's what we're trying to figure out. What is the maximum height of this function? Once we determine that, then we're going to basically repeat steps 3 and 4, but with our focus being on the absolute min. So we'll identify the candidates, and then once we figure out the candidates, we'll plug them all back into f of x to determine who is the lowest number of all the candidates. All right, we're going to try to decipher all of that lingo that we just put in our notebook and put it into action and make this closed interval test work for us. And let's see here. Of course, the directions say find the absolute maximum and minimum values of the function on the interval. So we're going to go with this. So let's say that my function is going to be x plus 2 cosine of x, and the closed interval will conveniently be 0 to 2 pi, which is probably the friendliest one they could have given me. So step 1 says we need to find the critical points. So let's calculate our derivative, and we'll set this bar equal to 0. Of course, this particular derivative will never be undefined, so we can eliminate that idea. And we'll get sine of x equals positive 1/2. And that occurs in the first and the second quadrants. I'm thinking 30 degrees, which is pi over 6. And I'm also thinking 150 degrees, which is 5 pi over 6. And we just want to make sure that everything we do in AP Calc is in radians. We may process the idea of degrees in our mind first, but we always need to take that one step further and put it in radians. So these right here are my critical points, and I have now accomplished step 1 on our list of things to do there. Now what I want to do is I want to use the first derivative test and figure out which intervals are increasing and decreasing. So let's see here. Whoa, where's that bear going? All right, let's try this. Okay, so there's my number line, and the only difference is instead of putting arrows on the end of my number line, I'm going to put closed points of 0 and 2 pi. Here's g prime. We'll put g on the bottom. We got pi over 6 and 5 pi over 6. Now, here's one of the coolest things about trig functions, and this rule that I'm going to share with you really only works with the sine and cosine curve. But what happens is this sine chart is guaranteed to oscillate. For instance, like if you knew this interval was positive, we would then know that this one's got to be negative and this one has to be positive. Or let me say it different. Maybe you knew this one was positive. Then you knew the one before it would have to be negative and the one after it would have to be negative. So really all we got to do is test one of the intervals, and then we can safely fill in the others. So the sines are guaranteed to oscillate. Now that is different. Yesterday we saw one where the signs didn't change. We had a false critical point, and that was because that's fairly common when you work with certain polynomials and such. But anyway, let's test a nice point. I'm going to plug in. I'm going to just make sure I can see the derivative. There it is. I'm going to plug in, let's see, I think pi is like one of the friendliest numbers to work with. So, and that falls within this interval right in here. So let's see, plug in a pi into the derivative and just show my work here for fun. Sine of pi is 0, so 1 minus 0 is just 1, so that's positive. All right, so what that proved is that g's increasing, and it also meant that g prime was negative, g's decreasing, and g prime was positive here, so g was increasing. Now what we want to do is we want to identify the candidates, and here's what I'm looking at. Now the function starts off at x equals 0, and it immediately increases, so here's a relative max. That also means that 0 is a candidate for being a min. It's a candidate, right? Because as we go from left to right, the function's increasing, so 0 would have to be lower than pi over 6. And then 5 pi over 6 is a relative min, which makes him a candidate for absolute min. And then last but not least, the function then increases until it hits our right endpoint of 2 pi. So 2 pi is a candidate for the absolute max. And so I'm just going to tackle my maxes first here. And we're going to take these candidates and we're going to plug them back into the original function so that we can figure out which one has the taller y value. A little competition between pi over 6 and 2 pi. And, oops, I should probably use g just to be official here. And let's see, I'm trying to plug it back into x plus the cosine of x, and there's a coefficient of 2 in there. So as I plug pi over 6 in there, it's a little awkward. I get pi over 6 plus 2 times radical 3 over 2. 2's cancel, and I'm going to get pi over 6 plus radical 3. Now, what in the world is this? As far as when you see pi over 6, it's approximately 1/2, and radical 3 is approximately like 1.7-ish. And so if you added those two numbers together, we'd get 2.2, and I should say approximately right there. Now, let's go compare that to 2 pi. We'll plug it back into the original. We'll get 2 pi plus 2 times, let's see, the cosine of 2 pi is going to be a 1. So this is 2 pi plus 2. Now as I'm estimating this, 2 pi, I'm thinking, well, it's bigger than 6, I know, and 6 plus 2 is going to be approximately 8. So here's my conclusion. I'm going to say that the absolute maximum value is 2 pi plus 2, okay? And I don't need to say anything about the derivative changing from this to that. That's only when we do relatives, okay? All right, let's go get the mins. Now remember, my candidates for the mins were going to be 0 and then 5 pi over 6. So let's go put them in a table and see if we can't figure out which one's lower. So let's make a nice table here. We've got our x's, we've got our g of x's, which happens to be x plus 2 cosine of x. And I'm going to plug in a 0 and then a 5 pi over 6. And again, the numbers get a little ugly, but we'll work through it. 0 plus 2, which is just 2, of course. And then 5 pi over 6 plus 2 times, let's see, the cosine of 5 pi over 6 is going to be negative radical 3 over 2. 2's cancel. 5 pi divided by 6 minus radical 3. Interesting. 5 times pi is about 15, probably closer to 16. And we'll say 15 divided by 6 is about, we'll say 2.5-ish minus 1.7-ish. Yeah, that's going to give me approximately 0.8-ish. And so this one's clearly smaller beyond a shadow of a doubt compared to that first one. So we're going to say our absolute minimum value, in other words, the height of the lowest point, is, let's see, 5 pi divided by 6 minus radical 3. So whatever that number is, that's our lowest point. Here's a real common example of an AP question that pertains to tonight's theme of absolute extrema. And they're kind of doing it the opposite way. They're giving me an incomplete equation. They're saying f of x is x to the fourth minus 4x cubed plus some mysterious x. So there's a constant at the end of that function, but we don't know who it is. And they're saying the absolute minimum value is 7. Now remember, the word value implies that 7 is the y-coordinate of the lowest point. And now they want me to determine the value of k. So my first trick is to try to use the first derivative test to find out the location. In other words, I want to know what's the x-coordinate of the absolute min, and then I'll pair that together with the y-coordinate that they gave me, and I can go find k. So that's my approach. So let's say, what's going on? All right, make sure I hit the right box here. All right, let's say f prime of x equals 4x cubed minus 12x squared. And we'll set that bar equal to 0. Of course, this derivative is never undefined. Pull out the 4x squared, and that leaves us with x minus 3 equals 0. I've got two critical points, one at 0 and one at 3. And notice it's not a closed interval, which seems awkward, but you're going to find out why here in a second. And there's f prime, and here's f, and I'll plug in a -1. Now notice this quantity right here is always going to be positive because of that squared sign. So I'm just going to plug my -1 in right here. -1 minus 3 is negative, so f's decreasing. Then I'll plug in like a 1. 1 minus 3 is again negative. And notice we did not get a sign change. We said earlier the trig functions guarantee a sign change, but with normal polynomials, that's not so much a guarantee. And then I'll pick something like a 4, and of course 4 minus 3 is going to be a positive. So finally, f's increasing. So just by reading my sign chart, here's what's happening. This polynomial, he must have started, it's either starting at positive infinity or negative infinity as far as its initial height. And so because of we're saying it's decreasing, that means it must have started at positive infinity for a height, you could say. And then it's decreasing, 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 and had a horizontal tangent at 0, but then continued to decrease. And then it bottomed out at 3. So this looks like my relative min for sure. And because it's the only turning point, I'm going to say it's an absolute min as well. And then from there, it just increased forever. So just to generate just a picture of what in the world we're talking about a picture that is decreasing, flattens out at 0, decreases some more until it hits 3, and then increases forever. So this is just a rough sketch of what f of x might look like. So here's what's happening. I know that ordered pair right there is 3, 7. So all I'm going to do is I'm going to plug that back into the original function and solve for k. So let's take a look. Let's sneak back up at the top here. And let's say, I'm going to say 7 equals 3 to the fourth minus 4 times 3 cubed plus k. And oh my gosh, 3 to the fourth I believe is 81, and minus, let's see, 4 times 27, 54, 108. So let's see, 81 minus 108, that's negative 27. Add the 27 over. I'm feeling 34 is the value of k, so that the absolute min is 7.